These are the lesson activities for section 2.1 for Math 204, differential equations. So we have the system r prime equals 2r minus 1.2 rf, and f prime equals negative f plus 0.9 rf. Initial conditions, r of 0 is 1 and f of 0 is 0.5. This is the same system from the demo. We want to try to sketch a solution curve in the RF plane, which is also called the phase plane, for time t equals 0 to t equals 1.5. And we're going to use a method similar to Euler's that we studied in chapter 1 with a step size of 0.5. So when t is 0, r is 1 and f is 0.5. Those were the given initial conditions. Okay, and I'm going to use a step size of 0.5. So this is going to be 0.5, 1, 1.5. Now I work my way across the table, filling it in. So r prime, remember, is 2r minus 1.2 rf, and f prime is negative f plus 0.9 rf. So we put in our calculator, we calculate r prime and f prime based on this r and this f value. So I have 2r, so 2 times 1, minus 1.2 times r, which is 1, times f, which is 0.5. And we get 1.4. Okay. Then I use those same r and f values, 1 and 0.5, and plug them into the f prime equation. So I have negative f, which is negative 0.5, plus 0.9 times r, which is 1, times f, which is 0.5, and we get negative 0.05. All right, and then my step size is 0.5. That was given. And then we calculate delta r and delta f. So delta r is just delta t times r prime. So I do r prime times delta t, 1.4 times 0.5 is 0.7. And delta f is delta t times f prime. So 0.5 times 0.05 is 0.025, and it's negative. Then I calculate my new r and my new f value by taking the old r value plus delta r and the old f value plus delta f. So I have 1 plus 0.7 is 1.7, and 0.5 plus negative 0.025 is 0.475. Now I calculate new r prime and f prime values using these formulas again, but new values of r and f. So 2r, so 2 times 1.7 minus 1.2 times r, which is 1.7, times f, which is 0.475, and you get 2.431. Okay, and then my f prime is going to be negative f, negative 0.475, plus 0.9 times r, which is 1.7, times f, which is 0.475, and we get 0.25175. And then calculate delta r and delta f by multiplying delta t times r prime. So delta f is going to be 0.125875, and delta r is 0.5 times 2.431, which is 1.2155. Okay. Now, get my new r and my new f by adding the old r to delta r and the old f to delta f. So 1.7 plus 1.2155 is 2.9155. and my old f plus delta f is 0.600875. And then I plug those new r and f values into the r prime and f prime equations. 2 times r, 2 times 2.9155 minus 1.2 times 2.9155 times f, which is 0.600875 is, and I have a lot of decimal places now, so I'm going to round this just for the purposes of writing it down. It's 3.72878. And I'm actually going to multiply that times 0.5 right now to get my delta r, which is going to be 1.86439. Okay, and then my f prime, that is negative f, so negative 0.600875 plus 0.9 times r, which is 2.9155 times f, 0.600875, and I get 0.97579, rounding because it's a really long decimal. And then I'm going to multiply that by 0.5, and I get 0.487895, rounded. Now, to get my new r and my new f, add old r to delta r and old f to delta f. So I have 2.9155 plus 1.86439, and I have 4.78 if I round to 2 decimal places. And then I take my old f, 0.600875, add my delta f, 0.487895, and I get 1.089. And I'm done. Okay, so those are the r values, the r and f values at t equals 1.5, which is what I was trying to get. Now I'm going to plot these in the RF plane. I want to plot these points. I'm just going to plot these in the RF plane. Okay, so r is on the horizontal axis, f is on the vertical axis. So 1, 0.5, that's my initial condition. And then 1.7, 0.475, something like that. And then 2.9 and 0.6, something like that. And then 4.78 and 1.089 is something like that. So there are my 4 points, one of them a given initial condition. This is a really tedious process, much better suited to a computer that can do a smaller step size and many, many more steps. Sort of follow that same curve. If we were to connect these, it kind of, and then you keep going and it makes this curve. I won't ask you to do that by hand again. I just want to make sure that like you can really understand what's happening. Here's the final result for t equals 0 to t equals about 5. I used a much smaller step size, and this is called a solution curve. We're going to use it to answer some questions. P represents the rabbit and fox populations at time t equals 0, and the arrow indicates the direction of time. And you can tell like R points. Okay, so based on the phase plane at left, what is R of 0 and F of 0? So R of 0, that is the coordinates of P are 1, 0.5 approximately, and that's an R, comma, an F, because R is on the horizontal and F is on the vertical. So R of 0 is 1, F of 0 is 0.5. What is the minimum number of rabbits over the time interval plotted? So rabbits are on the horizontal axis. So I want to find the point on this curve that is the furthest to the left. Okay, so the furthest point to the left might be like right here. And the horizontal coordinate, which is the R coordinate, looks like about 0.2, maybe 0.25. So the minimum number of rabbits over the time interval plotted would be R is approximately 0.25 rabbits. What is the maximum number of rabbits? That would be the point furthest to the right. So maybe right here. I think that looks like it happens at about 3.5. So R is approximately 3.5 at its maximum. Minimum number of foxes. Now, foxes is measured along the vertical axis. So I want to find the lowest point, which I'm thinking is actually this initial condition. Yeah. So the lowest point for foxes is when it started, which is 0.5. And the maximum number of foxes would be the highest point on the curve, which looks like it's about 4 foxes. Okay, so now I want to use the solution curve to sketch qualitative solution curves for R and F. So qualitative means I'm just looking for like shape, overall shape, increasing, decreasing behavior. This is not a really accurate sketch. So you have to remember that this is time, which does not show up in this picture. So the scale along the horizontal axis is unknown to us. We did not capture time in this phase portrait. So all I can tell is what happens qualitatively over some period, however long it takes to do this cycle. Okay, so if I start here, this is my initial condition. The number of rabbits is 1. So at time t equals 0, I know there is 1 rabbit. So that's the only exact point I know. And then I'm going to follow this curve around, and I'm going to track how many rabbits there are, right? So as I move this way, as I follow the curve, I'm moving to the right, which means R is increasing. So I'm moving right, moving right, moving right, moving right until about right here, when the number of rabbits hits its maximum, which is about 3.5. So I'm going to plot 3.5 rabbits. And so my function is increasing. The rabbits are increasing from 1 rabbit to 3.5 rabbits. I have no idea how much time passed in between there. That's why there is no scale on the t-axis. Okay, coming back to the phase portrait. Here's my maximum number of rabbits. Now, as I continue to follow the curve, now I'm moving left as I follow the curve, which means the number of rabbits is decreasing. So I'm moving left, moving left, moving left, moving left, moving left, moving left, moving left until maybe about here or here, right? When I hit the minimum number of rabbits, which we said was about 0.25. Okay. So from here, I moved left for a long time, but I have no idea how fast I drew this. I don't know how much time passed between here and here. So that's, again, there's no scale on the horizontal axis, on the t-axis here. But my next time I check in with the rabbits and find that they're at their minimum, they're at 0.25. So I'm drawing these like equally spaced just because it's convenient, but it could be that this one was over here or over here, and this one is over here or over here. But I can get a good sense of just plotting its maximum, where it started, it hits a maximum, then it hits a minimum, then let's see what happens. So from its minimum, which was about right here of 0.25, now as I follow the curve, I start moving right. I'm moving right, moving right, moving right, until I get back to 1 rabbit. So I plot that here. And then qualitatively, I can connect these and say, okay, it looks like my rabbit population started at 1, it increased to about 3.5, then the rabbits went into decline and they hit a minimum at about 0.25, and then they started to recover and are back where they started. I'll do a similar thing for foxes, except this time I'm looking at the vertical axis on the phase portrait. So I know my initial condition right here, P, the vertical location of point P is 0.5. So 0, 0.5 is my initial condition. Then I try to follow the curve. And as I'm moving along this curve, my pointer, or the point that I'm following, is moving up, right? It's moving up, moving up, moving up, moving up. Still moving up, still moving up. Moving up, moving up, moving up until here, when the number of foxes hits a maximum. And then they start to come back down. So from the initial time until they hit a maximum of 4, these are all increasing. The number of foxes is increasing, 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 increasing until it hits 4. So I'm going to put 4 as my next point here. I have no idea how much time passed, so I just put it on the next grid line because it's convenient. I don't know how much time passed between t equals 0 and when it hit this maximum. Okay, so now that it hits the maximum, now as I continue to follow the curve, my point, this little pointer, it's moving down, 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 until we get back to where we started at 0.5. So on my next spot, I'm going to put 0.5 again. And so my fox population does something like this. And really, these should have the same length of time that passed. So I might spread the foxes out over 1, 2, 3, a little bit more than that. So I'm going to put this here and this here. So that it should take the same amount of time because they're on the same phase portrait. So something like that. If we add several other solution curves to the RF plane that correspond to different initial conditions, we create something called a phase portrait for the system. This tells us information about the quality of the solutions to the system. The 2 single points that appear in the phase portrait, this one and this one, those correspond to equilibrium solutions that we found in the demo. So we know that R of t equals 0 and F of t equals 0. This is one equilibrium solution. If you start with 0 rabbits and 0 foxes, you will stay there for all time. And the other one was R of t equals F of t equals 10/9 and 5/3. So that was another way that the rabbits and foxes can live in a state of equilibrium. If you have 10/9 rabbits and 5/3 foxes, you will always have that many. They're living in a state of equilibrium. Okay, now we switch gears a little bit. We're going to model the motion of a mass attached to a spring when we ignore all forces on the mass except for the force of the spring. This is called a simple harmonic oscillator. Y of t is going to represent the position of the mass at time t, which is the quantity we're trying to model. For convenience, we're going to let y equals 0 be the position of rest. Y positive will be when the spring is stretched, and Y negative will be when the spring is compressed. So dy dt, if y represents position, then dy dt represents velocity. And the second derivative, d squared y over dt squared, represents acceleration. So remember, Newton's second law says force equals mass times acceleration. We want to replace the a in this equation with an appropriate expression involving y. So instead of a, acceleration, I'm going to write the second derivative. So f equals m times d squared y over dt squared. Hooke's law of springs states that the force exerted by a spring is proportional to the spring's displacement from its rest position. So force, F, is proportional, which just means a constant times displacement, and y is displacement or position. So I'm going to take my equation from part B, this equation, replace the F with negative ky. So I have negative k times y equals mass times, I think I'll just write this as y double prime, the second derivative. Now I'm going to take the equation from part C and solve for the second derivative. So y double prime equals negative k over m times y. And this is a model for a simple harmonic oscillator. And the equation from part D is called a second order differential equation because it has a second derivative in it. It appears that we have just a single dependent variable in this system, with displacement, or y. However, to determine the behavior of the mass over time, you would need two initial conditions, initial displacement and velocity. So we have a hidden variable in this equation, velocity, v. We're going to rewrite the second order differential equation, this one, as a system of first order differential equations where I now have two variables, y and v. So dy dt and dv dt, two different equations. So dv dt, the derivative of velocity, is just acceleration, or the second derivative of position. I have a formula for that, negative k over my, because the derivative of velocity is acceleration, or the second derivative of position, which I have. Okay, so I could write this as y double prime, or as v prime. Okay, so v prime, y double prime are the same. And then to fill out the system, I have to write dy dt, that's the derivative of position, which is just velocity. So dy dt equals v, and dv dt equals negative k over m times y. And that's it.